Okay, welcome everybody to session 2A. This is the special track on continuous planning, which was organised by Brian Williams and me, and we have 3 papers in this session. So our first paper, if we're ready, will be presented by Johannes Lohr, and that's a planning-based framework for controlling hybrid systems.
Thanks very much. Okay, hello everybody. I will talk about quite an interesting field that I've been working on together with Patrick and Thomas and Bernard Hebel. It's about the utilization of a planning algorithm for the control of real-world hybrid systems. For instance, the motion of a car or the attitude dynamics of a satellite or something that can be modeled by the use of differential equations. Therefore, we put a planner into such a loop structure with a hybrid system for the development of a planning-based framework for controlling hybrid systems. Let me give you a short outline of my presentation. I will talk about the motivation firstly, why do we want to use planning for hybrid system control. Then I will talk about how we can get from the continuous dynamics of the hybrid system to a domain model where we can actually plan on. Then I will talk about our approach, the domain predictive control approach, the architecture with this loop structure. I will show some exemplary simulation results and discuss the whole approach and a short talk on actually it will work. Okay, we're doing this research together with the space company EADS Asteron, and I have myself a space engineering background. And we have learned this morning in the Pyro talk that, for instance, landing of landers is a very challenging task for spacecraft. What you see here is a lunar lander and the X mission of ICAPS, and both spacecraft have to reach the goals in the absence of permanent communication links, but in the presence of failures and uncertainties. And there can happen a lot of things. For instance, there could be turbulences here in the atmosphere of Mars, so that we are currently in a state where we didn't expect to be, for instance. Or at the landing site, there's a crater, so that we cannot land where we want to land. Or a system failure occurs here, so that the thruster is faulty, for instance. Normally, in such a case, the mission could be lost because we cannot interact from Earth with the spacecraft to find a solution. That's why we want to find a framework where we can connect a planning algorithm with a hybrid system, so that the planning algorithm start thinking what is the best next suitable sequence of actions if we provide some goal information, for instance, the safe landing at the desired landing site, and the planner receives the actual current hybrid system state. Then again, the planner starts thinking what's the best next suitable actions to guide the hybrid system into a direction we want, into a state satisfying the goal condition. So this is the key idea. And if we want to develop such a framework, we have to focus on 3 main aspects here. First of all, we have to handle a hybrid system. That basically means we have a system with continuous dynamics, and which are captured by numerical state variables, and we have additional Boolean state variables, which define the mode of the hybrid system. Additionally, we want to make our spacecraft more autonomous. That means we have to do this computation on board. That means we have to reduce the computational effort as much as we can, because the computational resources, especially on spacecraft, are strictly limited. Then we want to make sure that we generate our decisions very quickly. So we have some real-time aspects here. And finally, we want to be reactive to exogenous events that are events which are not planned, which simply occur in the environment. For instance, if there occurs some obstacles in the environment, or if there occurs a system failure, we want to react on the system failure as well. So let's start in the beginning. What's a hybrid system? I think most of you are aware of that. but let's briefly go through the equation here. The hybrid system is basically a set of differential equations having a numerical state vector xn and for numerical containing all the numerical information, for instance the current position or the current velocity of car or the current angular rate of the satellite. And additionally, we have a logical state vector here defining the node of the hybrid system. This could be, for instance, the current actuator configuration or the current system dynamics that we are using underlying control feedback loops. And the planning task is now to find an input signal U. So if we want to change the numerical state variables here, we have to apply an external force, for instance, an external signal, for instance, a force or a torque. And the planning task is now to find a sequence of forces or torques or an external input signal U within the time window T8 to T that we transform the initial state into a state satisfying some load conditions. So this is the idea. We want to use a planner to generate the input signal, which then goes into the hybrid system and leads the hybrid system into a state satisfying some load conditions. Therefore, we basically have a three-step process. First of all, we anticipate some input fragments, for instance, the actuation of a thruster or a whole braking maneuver or something that we can imagine what could be useful to solve the control task. In the second step then, we solve the differential equations of the hybrid system, and in the third step, we generate the planning action here. Having preconditions, having a duration, and effects. We store the information about the homogeneous solution here, the state transition matrix, defined by this matrix exponential function here, and the inhomogeneous term, which is basically the impact of the anticipated input fragment, obtained here by the convolution of the dynamics with this anticipated input fragment, and finally the input fragment itself. The planner is now able to predict the future numerical state just by the evaluation of this equation here. So we are currently in a current state with a current position, a current velocity, for instance, and we know the future numerical state just by the multiplication of the current numerical state with the state transition matrix here, and with the addition of the inhomogeneous term. So this is a very simple equation we can express in a planning language, while we do this complex computation above here in a pre-processing step when we set up the domain. So this is how a planner can predict future numerical states. A set of leaf actions embodies now our domain model. The planning problem is still defined by the initial state where we currently are, and the goal state where we want to be. And if we look at this right graph here, these are the numerical states, and this is the time in the future. The planner can start stringing together actions and predicting future states until he has found a state which satisfies the goal conditions. Thereby generating a sequence of actions which can be translated back into the real world, into an input signal which will guide our hybrid system into a state satisfying the goal conditions. So this is the idea. So let's talk about the domain predictive control architecture, but before we go into detail there, let's remember the key aspect. We want to reduce the computational effort and complexity of this resulting planning problems. And we want to make sure that we generate our decisions very quickly. Basically, we are using their methods from model predictive control. So if we have a decision tree like this one here, so we are in an initial state, and we start exploring child nodes by applying all available actions we have, and we start exploring the decision tree here until we have found a state satisfying the goal condition. Then the lambda would probably be crashed because we don't have the time to search within an almost infinite state space. That's why we use a prediction horizon. So we only plan to a certain depth of the decision tree. For instance, here 4 steps. And additionally, we limit the number of states to be explored by the planning algorithm. The planner will then return a state which is good regarding heuristic information. And the state does not necessarily have to lie on the path towards the goal states, because in the second step, we just apply a subsequence of actions towards the state which was good regarding the heuristic information of the planning algorithm, and then we recede the horizon, or the horizon is receded, and we start exploring this subtree again. Again, we apply a subsequence of actions towards the state with best heuristic information. Again, the horizon is receded until we have spotted some states which are satisfying our goal conditions. And then we have found a solution. Of course, if we increase the number of states to be explored by the planning algorithm, and if we increase the planning to prediction horizon, then we will reduce the possibility to end up in a dead end. But this is finally simply defined by our computational resources we have available. So this was the autonomy aspect, and let's now talk about exogenous events and how we can handle obstacles in the environment or system failures, for instance. In domain predictive control, let's imagine the lander receives some new information about the environment or about the system itself. At each time we replan here, we can update the planning problem and the domain model. For instance, in the planning problem, the current initial state, if we are suddenly in a state where we didn't expect to be, this can easily happen if in the real world there are some dynamics which we have not modeled in the domain model. So we can update the initial state. Or we can update the goal information, for instance, if the landing site has changed. At the other hand, we can update the domain model itself. If there is a system failure, we can at least try to solve the control problem here, or the planning problem, by the use of the remaining feasible actions. So this is how we can try to increase the failure tolerance of our hybrid system. And this finally is the domain predictive control architecture. Let's briefly go through the loop here. A user or an external system defines or provides some goal information, S star. This goes into the planning problem. And we receive the current hybrid system state here. And the planner starts now predicting future states, generating a plan on the basis of the domain model here, so available here. This plan goes into the interpreter here, and will interpret it into a numerical input signal, for instance, a sequence of torques or forces, which will then guide the dynamic system into a direction we want. At the same time, the interpreter will provide a logical input signal, which changes the logical states of the plant. For instance, the sensor configuration here, or the actuator configuration, or the dynamics itself, which we are using the underlying feedback controller. Then the states will be measured here. So the measurement Y will go into an estimator. This is important in real-world applications. We have to estimate our real system states. And if this estimation is finally part of the goal conditions, we are done, and if not, we apply a subsequence of actions C here and update the current hybrid system state, which goes into the planning problem again. And we start the whole loop again until we have found a state satisfying the goal conditions. We also did some feasibility analysis. We have here the task that we have to bring a small ball, a dynamic system with a position and a velocity, on this tilt table here to a state satisfying some goal conditions. So a small flag here. and therefore we can incline the plate around 2 axes, leading to 9 different plate inclinations, each having a duration delta I of half a second. The holes here and the edges of the plate are simply modeled by preconditions, so we check in each state if we have fallen into a hole, and if not, we can continue with the planning process. We applied this problem and this domain to a planner to temporal fast downward, and let's see what the planner did. First of all, the planner found a solution. It's shown here, this thick black line guides the ball around the obstacles into the dome. And we see also the planned state actually, these are the black dots. And we see another interesting thing. We see intermediate found promising trajectories that are trajectories that lead into a state which was good regarding the heuristic information of temporal fast downward. So temporal fast downward did not plan directly to the dome, we planned into a state which was good regarding the heuristic information, and we started going to that direction until we have found a state which is better regarding the heuristic information. It's this one, and we go further into that direction around this obstacle until we found a state which is even better than regarding the heuristic information, and then finally we could plan directly into the goal, thereby generating an input signal, a sequence of plate inclinations in time, by a planning algorithm. So this sequence of plate inclinations will lead this ball into the goal state. Let's discuss the approach. Our experience with domain predictive control showed that we first of all had to find a balance between the planner performance and the model accuracy. Of course, we would like to have fine-grained discretized actions in time, but this will heavily increase plan length. At the other hand, of course, we would like to model each imaginable input fragment, but this will increase the number of available actions in each node of the decision graph. So the planner might fail to find a solution in such a huge decision tree. So the only thing we can do on the planning side here is to improve the heuristics, that we don't have to explore so many nodes before leading the hybrid system into a direction which is good, into a correct direction. And if there's still an imbalance here and we don't find the solution in a reasonable time, we have to increase the computing power to increase the prediction horizon or to increase the number of explored nodes. I would like to end with a short summary of pros and cons. Let's start at the cons side. I think the most important issue here is that we have to interstate our input fragments. That could be a very rough approximation of our real planned probabilities. Then we have a system dynamics, the domain model is the discrete version of our real-world system. That means the planner has only knowledge of the actually planned states and no knowledge of the trajectory in between two planned states. There could lie an obstacle, so there are some validation issues rising here. The computational effort is still quite high, and currently we can only cope with linear systems that are systems which we can model by the use of linear differential equations. But at the pro side, we have general problem formulation. We can apply this approach to a large number of problems. Then we can actively plan with system reconfigurations. We can handle restrictions in the state space. And we can at least try to increase the failure tolerance of systems by continuous replanning. Very briefly, a short outlook. We used this approach to predict or to generate plans that lead to acceleration profiles of landers to safely land at surfaces. Not only generating acceleration profiles, also generating a gain scheduling I don't want to go into detail here. If you're interested in this research, I will present this result on the Astrodynamic Specialist conferences here in August with the title Planning-Based Autonomous Lander Control. Okay, what's the take-home message? With domain predictive control, we basically have realized a planning-based feedback loop generating an input signal here, which accounts for restrictions in the state space, which accounts for changing system configurations. We can even actively trigger system reconfigurations, which accounts for changes in the environment or in the system itself. And all in all, we are processing here a lot of more information than in a normal control feedback loop. And from our point of view, this is a quite interesting approach. Thank you very much.
Okay, questions? Oh gosh, lots of questions.
So around slide 19, I think you said something that sounds like it's going in the direction of what would be called tracking performance in tracking controllers. Do you think that concept might apply here for your domain predictive controller?
Actually, tracking a reference input, which also changes, could be difficult. Currently, we are only trying to achieve a constant set point in future. So we have not. No, we didn't work on this reference tracking up to now. But we are thinking about that, and this could be an issue in future work, I think. And so we are right at the beginning right now.
Yeah. In standard control theory, time discretization is crucial to ensure the stability of the control. What about your approach to comment about the way to discretize time? I mean, usually in control theory, that would be neither high or too low.
Actually, yes. So the time discretization, we are doing a time discretization, it's true. And the actions even don't have to be discretized at the same time. Regarding stability, I think this was a question, right?
Yeah.
We have a predictive control approach. That means we are explicitly predicting future states. So we have knowledge of future states, and we can avoid to get into future states which are diverging, for instance. But the stability aspect is, of course, an important issue, and we will have some research on this in future work as well. Of course, it's a very good question.
Yes, Jonas, thanks for your talk. I had a question on slide 24, 23.
Okay.
You were displaying this trajectory that eventually you want to execute.
This one here?
Yeah, this one, exactly. And it seems to me there is some trajectory smoothing going on over there. So I was wondering how you can still guarantee that you're not falling into your hole after you've smoothed your trajectory.
Where do I have the trajectory smooth, actually?
Sorry?
Where?
Well, it seems that your trajectory is not point to point, right? It's like
yes, actually.
A second order interpolation going on.
No. It's because we have a dynamic system. It's because we have a system which has a mass and a velocity. So we're acting with a force, and we predict really the future numerical state, which is true if we apply the force, and this is actually the trajectory which the system will go if the system has a linear behavior. So this is not an interpolation, it's really the trajectory which is gone by the system itself.
Okay, so you can still guarantee that this will still be, let's say, a safe trajectory?
Of course, we have the validation issue that if there are some obstacles in between two planned states, then of course we cannot guarantee that this is a safe trajectory. So this is of course an issue, because that we have only knowledge of the planned states. Yes. But we're not doing an interpolation or trajectory.
No reference interpolation.
Yes.
Okay.
Just a question about the scalability of your approach. So how many states can you deal with, and how long is the horizon you can?
For this approach, I think we had a prediction horizon of, I think, 10 actions in future, and we explored something about 2,000 nodes in each plane depth. So this is a dimension of this approach.
What's the total length of the solution?
The total length of solution is 38. So the plan has 38 plane steps, but they are computed step by step because we plan in each planning step.
I think that there is a strong assumption in your approach. You assume that you have a finite set of available actions.
Yes.
Right?
Yes.
Is this assumption not too restrictive?
You're totally right. This is a restrictive assumption. We just have a finite set of actions, and if we have an action, if we have a system which could have continuous input signals, for instance, this would really be a rough approximation. But there are applications for that. For instance, in the maneuver-based control, we can, in one action, we can store a whole continuous maneuver. So we think that in this research area we could apply such an approach.
Okay, one last question, sir.
In every system's time discretization is an issue.
Yes.
I mean, if I take too far of a step to my right, I'll miss hitting the wall. So
Yes.
If there are zero, so detecting events when you take large steps is an issue, and I'm wondering if that's an issue when you do discretization. So basically the problem is that you take very large steps.
Yes.
You miss completely the fact that the continuous thing is crossing a particular threshold.
Yes, we could walk through an obstacle, for instance.
So
Yes.
you can,
Yes.
so do you take that into consideration when you're picking your, obviously you want as coarse discretization as possible. And so is that it, or are you just choosing a fine enough that it's not an issue?
Well, currently we just actually action with this constant duration, and if there's an obstacle with exactly in between two plane states, then we will miss that, and we will walk through the obstacle, and this is of course not possible. So this is really an issue we are working on.
Okay, we do have time for one very last thing.
Yeah, very shortly, how does it compare with standard control theory approaches or even reinforcement approaches? Because they tackle the same kind of problems.
Can you say that? Repeat
How
that, please.
does your approach compare with control theory approaches or reinforcement?
Oh, this is a very open question. I think, of course, normal or classical control approaches are much faster, for instance. This is one thing. Model predictive control is faster currently, and I think the interesting thing here is that we can process some unusual behavior of the system. For instance, if we have a control signal where we want to make sure that we have a logical consistency, for instance, if we have to preheat a thruster before we can activate this thruster, we can do that directly by this approach. So this is an advantage, but of course it's difficult to compare this approach directly to classical control approach.
Okay, I have to stop there. Thank you very much. Okay, so our next talk is bandit-based planning and learning in continuous action Markov decision processes, presented by Ari Weinstein.
Yes, so I won't be talking about the learning aspect of this talk, but it is in the paper if you're interested. Okay, so in terms of motivation, there are a lot of planning problems that we just heard that are fundamentally continuous, so often when we're controlling robots or doing a lot of other tasks. There are continuous actions and states that we have to deal with. On the other hand, a lot of the planning literature is concerned with dealing with domains that have discrete properties. So when this happens, a common approach is to discretize the continuous dimensions and then plan in that discretized domain. So this can be effective, but the problem is that it can be very wasteful in domains, especially ones that have a large number of dimensions because of the exponential blow up that you get in that situation. So in this talk, we're going to talk about efficient planning and continuous markup decision processes, and doing so natively without any sort of advanced predetermined discretization. So in terms of the overview, I'm going to talk about the discrete bandit problem, which is probably the most simple bandit problem that exists, and then the extension to the continuous setting. And from there, I'll go into markup decision process, as well as how to turn a bandit planner into a markup decision process planner. And then finally, I'll show parameterizal approach. Okay, so simplest planning problem that exists probably is called the KR bandit. In this setting, the agent is presented with a small finite number of arms, and each arm has an associated distribution of rewards. And so what we're interested in is finding the optimal arm A star, which is the highest expected reward. So the few values that we're interested in is the time t, the action is taken at that time, and then the reward that was achieved at that time as well. So we refer to regret as the difference between the reward that the agent achieved up to some point in time, between that and what it would have had if it had pulled the optimal arm at every time step. So in this setting, it turns out this simple equation, which is called UCB1, is optimal. It has a lot of regret that's logarithmic in time. And the way it works is it just pulls an arm that has maximum score, where the score is a combination of the reserved reward value and this other term here, which is called the bias term, which just gives a bonus to arms that have been sampled less frequently than others. So, and A is just the count of the amount of times that arm A has been sampled at time t. So that's what the discrete band setting is. So we can extend this setting to a continuum where there's not a finite set of k arms, but there's some infinite number of arms and there's some smoothness overall the expected rewards of arms that are nearby to each other. So commonly it's assumed to be Lipschitz or Holder or something like that. So the hierarchical optimistic optimization approach is one algorithm that's designed for use in the continuous bandit setting. So basically what it does is stochastic global optimization. So the way it works is that it starts with a root node that covers the entire action space, and it tries to make a decomposition of that space as time goes on. And as it does the decomposition, each node in that tree stores a value that estimates what the upper confidence bound on the reward for that region could be. So when it starts out, there's just a node, and it just takes some action. And after it takes an action, it splits the node into two, so we have two nodes that result from that. And from that point on, every time the algorithm is given the opportunity to take an action in the domain, it computes what's called a b-value, which I'll discuss in the next slide. And then it just follows b-values really from the root to some leaf. So on the last iteration of the algorithm, it could have started here and then taken the trajectory down to one of those leaves. So at every point that it takes a sample from the space, it bisects the leaf. So this picture on the right is if we present the algorithm with this bandit. So this is the set of arms that we can choose from, 0 to 1. Those arms have the associated reward between 0 and 1 with some noise added to it. This is a tree that's built in response. So this just represents the depth of the tree. And as you can see, what happens is sampling is done with very high density in the region of global maximum, global optimum. And so this is good because it is achieving both good regret as well as a very high resolution estimate of the region that has the global optimum. Okay, so now I'm going to go into the actual math of how the BE value is computed. Just like in UCB, there's a term that incorporates a mean value as well as some bias term for arms that haven't been sampled very often. In addition to that, there's another term which is just a volumetric bonus. So for each node in the tree, there's some bonus that corresponds to how large the region that node covers. So what happens is that for each the tree, we compute the upper confidence bound distribution, and then we recursively compute B. So B is a combination of two upper bound values. So it does is it takes the minimum of the two upper bounds that exist. And so this algorithm has optimal regret in this setting So this UCT is optimal, that's logarithmic in t, this is optimal credits in square root of t. So now we're going to move to Markov decision processes. This is probably familiar to a lot of people, but it's defined as having a set of states S, a set of actions A, transition distribution. So for every state action pair, there's a distribution over next states that can be arrived at. There's a deterministic reward function that maps to every state action pair to some real value, and then some discount factor gamma, which prioritizes immediate versus future reward. So in this setting, we're going to assume that A is infinitely large, because we're going to be planning continuous action spaces, and we're actually making no assumptions on this. So it can be finite, it can be discrete, or it can be continuous, or it can be a combination there. So in the algorithm, we are going to try and maximize the expected discounted finite return, which is this equation here. So to do that, we're going to be using sample-based planning. So in this setting, we assume that the agent has access to a generative model. So how the generative model works is that the agent can pass any query state action pair, and in return it gets back the reward and next state, where the next state is sampled from the transition distribution. So the domain tells the agent some state S to plan from. The agent queries the general model with a large number of state action pairs, with whatever information it wants. And then after it does that, normally after some timeout occurs, the agent informs the domain of what action it thinks is the best action to take A, resulting in a new state S, and this repeats over again. Okay, so now the question is, we have an algorithm that's designed for planning continuous bandit settings, and how do we apply it to continuous MVPs? So the approach I'm going to talk about here is called hierarchical open loop optimistic planning. It was introduced and analyzed theoretically in 2010. It's never been demonstrated, the performance has never been demonstrated empirically. So it does, it casts the n-step planning problem as a large optimization problem. So if the original domain is one action dimension, and we're planning 10 steps, then it's an n-dimensional optimization problem. And if the original planning problem is 2 action dimensions, it's a 2 n-dimension optimization problem. The planning is done open loop. So what we're trying to do is get an association between a sequence of actions and this discounted return I showed you previously. So what we do is we use who to optimize n-step planning, and then we use the first recommended action, and then we start planning over. So if we're doing one step of look ahead in a whole lot, we're just maximizing the immediate reward R1. And this is just a one-dimensional function that we're trying to optimize. And it's really equivalent to the bandit setting. So if we're doing this, we're not really doing anything special for any of these. But if we're doing 2 steps of look ahead, now we're trying to maximize R1 plus gamma R2, where R1 is the immediate reward we get, and R2 is the reward that we get at the following step. So here the horizontal axis represents the immediate action, and the vertical axis will represent the next action we take in sequence. And so we can keep doing this, we can keep generalizing this out. If we do 2 steps of look ahead, we're now trying to do optimization in 3-dimensional space. So what are the properties of the algorithm? So like who, pull-out improves at a rate of O squared of t. And this is independent of the action dimension and the depth that we're planning to. But this is only true as the number of queries that we're using becomes very, very large. So in most settings, those values do actually matter. On the other hand, because we're doing open loop control, it means that the algorithm is truly agnostic to state. So the size of state dimension and whether it's discrete, continuous, or hybrid doesn't matter at all. As an anytime planner, we can stop at any point and ask for what the best action it thinks it has, and the performance will continually improve as we give it more time. Finally, one negative thing is that because it's an open loop planner, it can have arbitrarily bad performance in domains of particular structures if they are noisy. So now I'm going to compare rollout to UCT. So for those who aren't familiar, UCT is an algorithm that's become very popular over the past few years. It stands for upper confidence bounds applied to trees, and it is also a sample-based planning algorithm that uses results from bandit literature. So just as rollout is an algorithm that's designed for continuous MVPs, UCT has UCT1 inside of it that controls the policy for finite MVPs. And just to point out that it is a very powerful algorithm, and it's considered state-of-the-art for a lot of areas, including planning and code. So the domains I'm going to show, they are continuous. So in order to leverage UCT in those domains, we have to use some coarse discretization over both the state and action spaces. So the two domains that I'm going to show results for, they're sort of canonical control domains. One is called the double integrated domain, where we're controlling a point